Syzygy, episode 20. Can you photograph a black hole? And welcome back to another edition of the Syzygy podcast. This is episode 20, and this week we're talking about a bunch of astronomers who are attempting to take probably the most difficult photograph in the history of photographs of all kinds. I mean, you know what it's like when you go out with your camera and, I don't know, you're trying to take a picture of a beautiful landscape or your kids running around or a dog doing something silly. And it's really hard because if you miss that moment or if you get it just at the wrong angle, then it's gone. Well, imagine that, but multiplied like a billion, because these astronomers are attempting to take a picture of the supermassive black hole at the center of our galaxy. I know. My name's Chris Stewart. Joining me at the microphone, my co-host, as ever, Dr. Emily Brunsden. Hi, Emily.
Hello.
So before we get into the whole black hole stuff, and this just blows my mind, we've got a lot to unpack around this story. But before we do, there was a lovely little thing that I saw on Twitter this morning. A friend of the show, Thomas, sent through a link to something from NASA's Fermi satellite people, Fermi telescope people. They've come up with a whole bunch of new constellations in the night sky, which I think is really nice. They've gone through what's Fermi looking at the sky in?
So it's looking at really, really high energies. So we're looking at gamma rays.
So this is not optical that they're looking at. It's not looking up at the sky and going, that star there and that star there, that star there. Let's put them together into a pattern that vaguely looks like a crab. They've taken all of these really high gamma ray sources, which we probably can't see with the naked eye, right?
No, and they're not stars
right.
either.
So what would they be?
So they're really high energy environments. So things like the outputs from black holes can produce gamma rays. Sometimes supernova explosions, depending on the angles and the how long ago they were. So like super high energy environments within the universe.
So they've taken these maps of the high energy night sky, and they've gone, well, look, if stars can make constellations, then we can make our own constellations. What should we find? And they had to look through and they've come up with their own set of constellations. I'll put the link in the show notes. You can go and explore it and sort of scan around and click on them. They got things like Albert Einstein's face and the TARDIS from Doctor Who and just all of these. And I think these are even better than the old constellations, actually. We should stick with these and, if necessary, create a whole new astrology out of them. You know, it'll just be just as meaningful.
That would be fantastic.
I think it'd be great.
Yeah.
You know, born in the year of the TARDIS, I think, with Einstein rising. I think that'd be great. Anyway, link in the show notes. Go and check that out. It's quite fun. But back to the topic du jour. There is a story which has been doing the rounds, which is an interesting one because it's a work in progress. This is about a group of astronomers who are attempting to photograph, take an image of a black hole, and not just any old black hole. The black hole at the center of our galaxy. Supermassive, big thing. We've talked about it on the podcast before. The thing about black holes, though, they're really quite difficult to see in some ways. In other ways, not so much. So, Emily, help us figure this one out. What's going on?
So the thing I love about this story is that this is quite different for Syzygy, actually, because we normally are reporting on a piece of science that's just been published, that new results, it's all very exciting. And today's story is kind of about something that's probably about to come out after years and years and years of hard work. So if you sort of see this news story come up in the next few months, which I wouldn't be surprised if it doesn't, if the image that we're talking about hits the press, then you guys are getting a super early advance
this is a
understanding of what's actually things that are going on.
But the reason it's a preview is inherent in the story. This isn't just a bunch of astronomers going, oh, yeah, we're working on it, stay tuned. It's actually a little bit more interesting than that, and we'll hopefully touch on that because it's part of the process of the science, part of the process of the research is that there's this really long intermediate period of we are looking at the data in a bunch of different ways. Anyway, let's back right up. Who are we talking about for a start?
So this is a massive international collaboration, actually. It involves dozens of telescopes and many, many different observatories across the whole world. So it's a huge effort. It's kind of being led by groups MIT, Harvard, MIT Haystack Observatory and Harvard, the Max Planck Institute for Radio Astronomy in Germany. They're the two data centers particularly that are looking at what's coming off the telescope. But of course, there's about at least 13, I think I counted, different observatories around the world, and many more than that in terms of number of telescopes. So it's a huge coordinated effort.
And it's not just, I mean, that makes it sound a little bit like there's a lot of astronomers who are all looking at the same thing and seeing who can come up with a picture. But it's much more complicated than that, because the thing that they're trying to do, take this picture of an object at the center of the galaxy. Now, when we talk about supermassive black holes, that sounds really big, but they're actually trying to image something which is ludicrously small. And there's only a few ways that you can think about doing that. One is to build an enormous telescope. The other is to collaborate and to combine forces across a bunch of different telescopes. So we're going to need to talk about that as well. Where should we start? How do we get into this story?
Okay, so let's start talking about what instrument I think they're using. And
okay,
it's called the Event Horizon Telescope.
Good name.
It's not a single telescope. And, well, it's actually this collaboration of all these different telescopes, because there's a wonderful thing you can do with light, and that is if you are able to, you could build a huge telescope, right? And we've built huge telescopes. We've got one that's 11 meters in diameter, mirror, for example, that works in optical wavelengths. But when you get down to very, very low frequencies and very long wavelengths, you can start to do really interesting things with your light.
Now, we're talking about when you're talking long wavelengths, we're talking radio waves here.
Radio waves and microwaves. So microwaves are a little bit shorter than your traditional radio waves. And what you can actually do is, instead of having a giant telescope, you can actually use two telescopes and combine the information to pretend you've got a giant telescope that's as big as the distance between them.
It's a little bit like one telescope is on one edge of your pretend huge dish, and the other telescope is on the other end of the pretend huge dish. It's a little bit like that you can sort of say, well, the distance between them, if we combine our forces, it's kind of like we've got a telescope that big.
Yeah, and it's a wonderful technique called interferometry. So, for example, on the Astro campus here at York, we've got 2 3-meter diameter radio dishes. Now, you can use each of those dishes independently, and you can gather the light from the universe, and that's really interesting to do.
And 3 meters is a reasonable size for a student telescope. That's okay.
Brilliant for us. Yeah, it's really fun. But what we can do is, those two telescopes happen to be about 15, 20 meters apart. So if we were to combine the signals from those two telescopes, we could actually achieve resolution of our images that's as if we had a 20-meter telescope.
Which is much better.
Yeah.
That's much better. Now, you're not going to be collecting all of that radiation. I mean, if you did have a 20-meter dish, then you'd be collecting 20-meter diameters worth of the radio waves or the microwaves coming down and bouncing off and coming into your detector. You're not getting all of that, but you're still able to get the resolution of that size of telescope. That's what you're saying.
Yes, exactly. Yeah. So you can kind of cheat a little bit if you like. And we've been doing this in radio astronomy for a very, very long time. And in fact, we have a whole structure which is called VLBI. And VLBI stands for Very Long Baseline Interferometry. So going backwards, we're talking about interferometry, which is the process of combining signals. The baseline is the distance that you put between two telescopes, and very long. Well,
it's very long. In that wonderful way that astronomers like to name things. Like, how long is this? It's very long. All right. Put it in the title then.
So when we talk about the Event Horizon Telescope, it's been described, and this is by the director of the project, as the biggest telescope in the history of humanity.
How big are we talking about? I mean, you were talking about, 20 meters walking between the dishes that you've got down at the Astro campus here on York University. That's 20 meters. How big is this?
Basically the size of the Earth.
Right. Okay. Okay. And it's a bit difficult to think of something bigger than that unless you're going to start putting stuff in space, which I guess is possible. But if you're going to be down on the ground, that's as big as you're going to get.
Exactly.
Right.
So this network, if you like, the Event Horizon Telescope, uses lots of telescopes from the US, from Mexico. There's some in Europe, there's some in Chile, and there's even one at the South Pole.
Now, correct me if I'm wrong. It needs to be this big, doesn't it? Because when you're talking about the size of the telescope, size is important because the bigger you are, the more finely grained detail you can make out, right? And we're looking at something, or they're looking at something, which is incredibly fine. You know, they're not trying to image the center bulge of the galaxy. They're trying to image the center of the galaxy.
Yeah.
So it's got to be
black
that
hole
big.
that's there. Yeah. So look, if you recall back when we talked about the black hole, the supermassive black hole at the center of our galaxy a few episodes ago, we were looking at the orbit of S2, which was this star that hurtles around this black hole. Now, to remind you a little bit of what event horizon actually means, the event horizon is kind of one way that we use to measure the size, if you like, of a black hole.
Yeah, because black holes are weird, right?
Yeah.
They're a region of stupidly strong gravity, but where the universe is kind of, folded in on itself, and everything else that we know about space and matter and stuff has just gone. And we're left with just this almost pure gravity, incredibly strong field. And so if you're going to talk about the size of the black hole, you've got to pick something. And that something, in this case, the event horizon, is, all right, well, where can light get out and where can't it? Beyond this line, the event horizon, nothing's getting out, not even light.
Because light is distorted by gravity, right? But light has to obey gravity just like we do. So basically the pull of gravity in the black hole is so strong that light can never escape from that gravitational tug. Then so that forms kind of a sphere, if you like, this which we call the event horizon. And more technically, we call the radius of that event horizon the Schwarzschild radius. And if you think about the size of that, it's pretty small.
How big are we talking for a supermassive black hole like the one that's at the center of the galaxy?
So we're talking about 0.08 astronomical units.
0.08. So rounding that up to the nearest, that's 10% of the way from the sun to the Earth.
Yeah.
Yeah. So that's big, but it's like looking in detail at a largish star at the center of the galaxy.
Yeah, and you've got billions of times the mass of the sun in that tiny, tiny area, which is why the gravity is so horrendously strong.
Yeah. So that kind of gives a sense of why we need a telescope this big. We're looking at something very far away. And the center of the galaxy, how far away are we talking? It's like 20-something thousand light years?
Well, actually, I've got a new measurement.
Hey!
Because we talked about S2, the star that was hurtling around the center. So from that, we've been able to determine an updated and even more accurate distance to our friendly black hole at the center.
Hot off the presses.
Yeah. So it's 7.94 plus or minus 0.42 kiloparsecs.
Okay.
So that's...
I never assimilated parsecs, so...
They sound quite science fiction, don't they?
Yeah.
So kiloparsecs, so it's thousands of parsecs. So, roughly 8,000 parsecs. A parsec is a few light years, 3.2-ish light years. So if you think about the distance to our closest star, that's kind of a few light years away. So you can approximate it with maybe the distance to our nearest star as a parsec.
So about 8,000 times. So we're talking in the 20,000s light years.
Yes.
Which is really interesting because, we're talking within our own galaxy. This galaxy, one of billions and billions and billions of galaxies in the universe that we know. But this is just this local one. And the center of the galaxy is still, call it 25-ish thousand light years away, which means that this picture that the astronomers are trying to take is with light that left the center of the galaxy over 20,000 years ago, which is nuts. But there we are. Astronomers get used to dealing with things that are a bit nuts. Yeah.
And in terms of scale, of size of thing, I mean, the size of the object that we're trying to image here has been, if you scale it to looking at, say, something on the surface of the moon, if we were trying to look at the same resolution, then we've been trying to be looking at something the size of a donut.
And that's hard.
Yeah.
Okay.
That's really, really hard.
Yeah. So anyone who's attempting to do this has got their work cut out for them. This is a story which began quite a long time ago. Right?
Yeah,
these astronomers have been doing this for more than a decade now.
Yeah. So what the wonderful thing about these kind of observations is that, so the combining two signals from two different telescopes sounds like it's just easy. Let's just shove them together and see what we get. In reality, it's really hard, and it requires a really sophisticated computational process to do that. It's called correlation. And actually, when we started this project more than a decade ago, we didn't have the computational power to be able to achieve what we wanted to achieve.
Seems to be a lot of that in astronomy at the moment. Just do it. We know how to do it. We just don't know how to do that bit of it. So collect the data and we'll worry about that later.
But we know that computers have been improving, and they've been improving at a moderately predictable rate over the last tens of years. So we kind of said, well, we'll start working on it now and hope that the computers catch up by the time we're ready to start taking the images.
Plus, I guess if you're talking about correlating data, joining forces of telescopes across the planet, that involves a lot of money, a lot of effort, asking for a lot of telescope time on a lot of different machines. You'd need to do a bit of a trial run first, which I think is what happened back in about 2007, wasn't it? That these astronomers got 3 telescopes and put them together and said, all right, let's have a look at the center of the galaxy, just as a proof of principle. And see what we can see. And what they saw was interesting, not sure, can see something.
Kind of like a fuzziness.
Yeah.
It's like, okay, well, this is encouraging. Basically.
Which is that great result that you get in science where, if only we had a bit more money and a bit more time, and could we do this bigger? And if that works, then you've got, that's your next couple of decades stretching out ahead of you as far as science is concerned.
And once you've got that Nature paper, which they got and for the original image, then it's much, much easier to convince other people to come on board and spend some money on actually trying to do this image properly.
So there was the trial run in 2007 with a few telescopes. Fast forward 10 years and you've got a much bigger collaboration going on. This one that you're talking about that involves telescopes across the world, including down at the South Pole. So where's it at? What's happening?
So all the telescopes got together and took some images over the course of 2017. There were it's hard because not only have you got to get all your telescopes to have clear weather at the same time and be operational at the same time. One telescope goes down for maintenance, then that kind of stymies a little bit what you're trying to do. But they also needed to have things like really super precise atomic clocks, because what's wonderful about the system is that they're not connected by kind of like Wi-Fi or anything like that. The data are recorded at each of the telescopes, and then that data has to be put together by literally flying the hard drives to a central location, and then the astronomers putting back the data.
Although, as it turns out, there's a wonderful quote, and I can't remember who first said it, but someone once said, never underestimate the bandwidth of a bunch of tapes or hard drives on the back of a truck going down the highway. You can shift a lot of data that way that would be a bit trickier through conventional electronic and optical pipes.
Indeed,
Yeah, you are. You're talking about an enormous amount of data on hard drives being literally carried around the world to get together and correlate.
Yeah. So when you put that data back together, you have to know super precisely exactly when which signals came into which telescope.
Because that's the whole point, isn't it? In order to make this telescope the size of the Earth, you've got to be able to say this bit of data here in North America came at the same time as this bit of data that came to Antarctica, as this bit of time that came to Europe, as this bit of data that came to South Africa. You've got to be able to say all of these bits are the same.
And part of that is because of the wavelength of light that we're using. So interferometry is actually looking at, imagine you've got like your squiggle of light that's coming towards you. And in the case of the millimeter or microwave region that we're looking at, they've chosen a band of 1.3 millimeters. So that's how long your wavelength of light is, right? And what all these telescopes are doing are measuring at what phase that bit of light came to their telescope. So did it come when there was a peak in the light? Did it come when there was a trough? But you've only got 1.3 millimeters of wavelength to play with there. And now can you imagine the speed of light
tuned.
that it's coming at you, this 1.3 millimeters is coming at you at the speed of light. So the precision required on your time measurement is just really, really high.
So this is hard. I mean, there's no way to overstate this. This is hard. This is probably the hardest photograph that has ever been taken in the history of all photographs ever. But it's worth a shot, right?
Oh, yeah.
Because here is an object which we are pretty sure it's there. And that object has a name, doesn't it? We're talking, what is it, Sagittarius A star?
Yes.
That's the official name given to the supermassive black hole at the center of the galaxy, because it's in the constellation Sagittarius, and the star refers to really high energy thing.
Yeah, because that's how we originally found it. We didn't go out there looking for a black hole. We went out there looking for really high energy light in both the high energy spectrum, like what Fermi does, and also in the radio spectrum.
Right. So there's this thing, and we've got all sorts of indirect evidence to say that it's there. And we've talked about some of this before, you know, stars going around at ludicrously high speeds, you know, speeds that you just don't see stars doing. So we know that there's something there, and we know where it is. But this is different. This would be saying, let's look at it. Let's take a picture of it. Immediate question, how do you take a picture of something that by definition is black?
So this is where it gets quite interesting because, of course, the object itself, the black hole, is not putting out any light. Light can't escape. But it turns out it has a shadow.
Okay.
And it happens to be in a part of the galaxy, well, it happens to be, it's defining a part of the galaxy where there's huge numbers of stars as well. So the traditional kind of image, if you like, of a black hole is kind of this black sphere. And it's not because that's the color of the object and it's got a surface. It's because everything behind it is being blocked out by this shadow.
Yeah, any light that would be coming, you know, past the black hole just gets completely bent and either absorbed or, you know, flung out at some incredible...
Yeah, and that shadow is about 10 times larger than the event horizon itself. So it means that you're going to have something that's 0.8 times the distance between the sun and the Earth. So it's still really, really small thing.
So you should be able to see this shadow, again, very, very small, but what they're hoping is that they'll be able to image this larger shadow of the event horizon, which is where light from around and behind the supermassive black hole is not going to get past.
And even more than that, after you at the edge of the shadow, then you're going to see this ring. And this is the ring of all the light that's been warped. And so it forms this kind of glowing surface around the edge of the black hole.
And these are the sorts of images that we've seen a few times in popular depictions of black holes, which seem to have been getting better and better over time. Like there was a great film from the 1980s. I don't know if you ever saw it, called The Black Hole. It was a Disney movie. And the imagery from that was literally coloured water going down a plug hole. You know, you can look at it and go, I know what that is. That's my kitchen sink, right? It's not like that. It's not a big whirlpool sucking everything in. Through to Interstellar, which was just a couple of years ago, where they actually got, you know, world-leading astronomers and theoretical cosmologists to figure out what would a black hole actually look like. And you get these much more interesting structures of black blobs with interesting rings around them and stuff. This is now to the next level of, well, okay, let's see if we can find this shadow with a bright ring around it.
Yeah, and what would be even more exciting, what we're hoping to see, is that that ring is not actually a uniform brightness ring. If it's a crescent, then that actually starts to tell us a little bit of physics of what's going on as well. Because if what we're hoping to see is if the crescent, because there's the black hole should be, in theory, rotating. Right. This is part of Hawking started off with these wonderful theories of black holes. How do they work? And then these theories were further developed by Kerr and so on, and into how do black holes work when they rotate.
And let's be clear. It's very likely. In fact, it's certain that the black hole would be rotating, because we're talking about something which is collapsed down. When the mass reaches a certain density, it collapses down under its own gravity. And we know that whatever rotation it had before that collapse has got to be conserved. And so all the theories of black holes are saying, well, whatever that black hole is, it's still got some rotation. That is one good analogy to water going down a plug hole. The reason water going down a plug hole spins much faster near the hole itself is because tiny bit of rotation in the water gets much, much more amplified the closer down to the plug hole you get. And so we expect this black hole to be rotating.
Yeah, and we could kind of see that from it's a part of the Doppler effect. So the Doppler effect, astronomers love the Doppler effect. It's just one of the great things that light does. But basically, the light that's coming towards us from that ring should be brighter than the light that's going away from us because it's changed in wavelength.
Right. So you're saying that looking at this shadow with the bright ring around it, on one side, assuming that this is rotating, on one side we should see it brighter than the other, and that would make this ring look a little bit more like a crescent, where it's dark on one side, bright on the other.
Yeah.
Right.
Very, very cool.
Yeah.
And then moving outwards from that ring, we see, and we have seen some of the lensing effects from the black hole. So this is when instead of having a star, which is a nice little circular blob, you start to see lenses, which are like sort of streaks, curved streaks going across the sky. We see this in other galaxies, and even in the space between galaxies, where galaxies themselves are being lensed by dark matter.
And when you say lens, you mean that because of the gravity is so strong, it's bending light that's coming near it in a similar way to the way a glass lens bends light around to form an image. You can see the same kind of effect near very massive objects like black holes, where the light from behind it gets bent around it to create images, and sometimes really quite peculiar images.
Yeah.
And it's called gravitational lensing. Yeah.
Yeah, so you sort of might see some arcs of the things that are near the center of the black hole, or near the black hole itself. And then, of course, we've got S2. So for perspective, S2, we can remind ourselves is orbiting at at the moment, about 120 astronomical units away.
Right, that's the star that's been tracked going incredibly quickly around the black hole.
So that's kind of an interesting sort of way you might build up this picture, this image of what this black hole might look like.
So all of this is very theoretical, right? We said that back in 2007, this team of astronomers did its trial run and saw something. There's we can see something there in the middle of the galaxy. Let's do some more work for the next 10 years. And in 2017, this huge effort from all over the world involving incredibly precisely timed observations from a bunch of different telescopes spread across the planet. Lots of hard drives put on the back of a truck and sent down the road for correlation. Mm-hmm. So what? What's the answer?
Well, we're still working on it, I think is really the answer. So the last observations were taken in about December, and the data was sent off to do different processing stations. So this is where Haystack, MIT's Haystack Observatory and the Max Planck Radio Institute in Germany are looking at the data. And they have on the order of, I think it's 800 computer processing units working on the data to try and put it all back together from all these different telescopes. And it takes time is the next thing, because not only does it take computer processing time, but this is the first time we've made an image of the black hole at the center of the galaxy like this. So we've got to work out how to actually make that image work.
And that's a lot of processing power. This is not something that your iPhone can just do in its spare time when you snap a picture of your kids running around outside in the blink of an eye. This is an enormous amount of processing. And it's also putting together data from all of these different telescopes, making sure that you can figure out which bits of data line up. And then also, presumably, you've got to make some assumptions about how to put that image together. It's not really obvious how to create the image at the end.
Yeah, because I think here we have to be very honest and say, actually, a radio image is not really like taking a photograph. So when you go out and take a photograph all the pixels in your camera, get illuminated, and you can put back together the color information and so on. And you snap your lens, it's done, it's gone, and you take the photo.
Yeah, to within a certain amount of trickery within modern cameras, there's a fairly good one-to-one correlation between what you see over there and the light that enters through the lens of the camera and ends up on the sensor and turns into a photograph. To within some reasonable limits, what you see is what you get. And it's not quite the same with radio, is it?
No, radio, I like to think of it as kind of a little bit more things like paint by numbers in a sense, because what you are getting is you are looking at how intense is the radio signal at a particular tiny point in sky at a particular time. And so you take in your data and you actually convert it to a digital electronic signal instantly. And that's what allows you to do all these wonderful things with interferometry. But it means that you don't just sort of have a picture of whatever this black hole is pop up on your computer at the end of the observation.
And it's even more complicated than that, though, isn't it? Because these are all ground-based telescopes, so they're looking through the atmosphere in different places. So you've got to adjust for some of that, right? There are atmospheric effects. They're looking from slightly different angles and slightly different places. They're looking through the galaxy with all sorts of stuff in the way. So you've got to account for all of that in order to be able to put this together into something like a final image. There's a lot of assumptions and theories and stuff that's going into making this, which is why there's not just one team doing it, right? Because this is the other thing. If everyone could just throw their processing power at, we need one image, that'd be one thing. But no, they're doing this in multiple places because they want to be absolutely sure, right? They want to know that team over here looking at this data, we've come up with an image. Well, is that the only way that this could be done? What about we get another team over here doing the same thing and we don't let them talk to each other and we see if they come up with the same image? And if they do, then we're pretty sure we know what we're looking at. If they don't, maybe we've got to go back to the drawing board on some of these assumptions. So it's incredibly hard.
It really is. So from December last year, I think people are working really hard. And my feeling is maybe we're going to see some results of this pretty soon, which is really exciting.
And the scuttlebutt around astronomical circles. I mean, there's been a few articles which have come out over the last several months kind of saying, hey, there's this really big story coming, which maybe suggests there's a little bit of seeding of excitement happening. So fingers crossed, within a few months, we'll know what the answer is. Is there a picture? And if there is, what does it look like?
Yeah, and I think there's even more that we can answer with that, because it's all very well to say, okay, there's a thing at the center of our galaxy it's hard to take a picture of, so let's work really hard and take a picture of. Of course, there's more to it, what we want to do about it than that. It is more than a picture.
Yeah.
So I think it's really important to remember that there is physics going on here that we're trying to learn. So we mentioned, for example, the rotation of the black hole. We were trying to learn about that. But we also want to test general relativity. We were testing it with S2, the star, but let's test it even closer to the black hole.
Yeah, I mean, the best place to test Einstein's general relativity is in the most extreme gravitational environments you can find. Well, it's difficult to find more extreme than the edge of a supermassive black hole. So if you can find that edge and take a picture of it and look at it and get some data from it, then by its very nature, you're going to be able to learn something about how well are our theories holding up at this point. And so far, Einstein's done really well with all the tests we can throw at it. But here's another really good and brand new test bed that we can put it on.
Yeah. I think another thing about this supermassive black hole is it's very easy to put it aside and say, well, this is a wonderful exotic thing, but does it really have any sort of impact on us? Particularly, you think about our solar system and the calmness of our sort of planets going around the sun. And what we need to remember is that this black hole at the center of a galaxy shaped and formed our entire galaxy.
How do you mean?
So it's in a constant feedback process with the material in our galaxy. That black hole's spitting out energy, and it's also taking in matter as well. So the whole evolution of our galaxy is intrinsically tied to what this supermassive black hole has been doing.
Right. This thing hasn't just been sitting there doing its thing quietly for all of time. It goes in and out of different cycles and phases. It gobbles up some stuff. It spits out some stuff. And what you seem to be saying is that that's not just going to affect its immediate local area. That has an effect on the entire galaxy.
Yeah, so to understand how our whole galaxy evolves, we need to understand what's going on in the black hole to understand these cycles and phases. So that's pretty cool.
That is pretty cool. So taking a picture of this thing will help us to understand everything right back to even our own little local quiet environment here on the 2/3 the way out along a spiral arm of the galaxy.
So what we're thinking about also with this picture is that it may well have some significance in a human way, a bit like the pale blue dot picture has.
Yeah, pale blue dot is that incredibly famous picture which was taken by Voyager, wasn't
Voyager
it?
1, yeah.
Voyager 1, on its way out of the solar system, they turned the cameras back towards the Earth and took a picture. And this is a picture which is looking back across the solar system, and it sees the Earth as this tiny little pale blue dot.
Yeah, it's less than a pixel in the image.
And the amazing thing about this image is that it in some way sort of captures all of humanity in this pale blue dot, in this tiny little dot in this picture, and makes you think, wow, goodness, we're a bit small, aren't we?
Yeah.
And
so
space is big, isn't it?
Space is really big. And in some ways, taking a picture of this black hole is reminding us of a little bit of our own humanity and our smallness, I guess, in the scale and our place in the entire universe.
And that's it for another edition of Syzygy. If you've enjoyed the show, then you can get in contact with us in all sorts of different ways. One way is through Twitter. Emily, you're the Twitter goddess. How do they get in touch with us on Twitter?
Love Twitter. So you can tweet at us at SyzygyPod, SYZYGY pod. You can also follow Twitter and follow the links to our website.
That's right, syzygy.fm, and you can find all the show notes, all the past episodes. Go and just get your absolute fix of Syzygy stuff. We're on Facebook, of course. Just search for us, the Syzygy Podcast, or facebook.com/SyzygyPod, I believe, works as well. We are on Instagram. We're just getting all of the social media. We're collecting them all now, so you can find us on Instagram as well. Or you can just go to our website, syzygy.fm, and if you want to say hi, then you can fill in the contact details there. Send us some questions. We might feature them on a future show. Speaking of future shows, we've got something interesting coming up. We're going to be doing a live show. Now, for those of you who are listening across the world, this might be a little bit difficult, but if you're in the local area of York, York, UK, that's not York anywhere else, York, UK, then we're going to be taking part in a little local research evening called Your Night. YORNIGHT. And we're going to be doing a live show at Your Night on Saturday the 17th of November. So we don't know the full details yet. This is all very, very brand new, hot off the presses. But if you are interested and you're in the area, check out our website, syzygy.fm. We'll put news up on there, all the details as it becomes known. But come along if you're in the area. It's going to be great fun. We'll have a bit of a chat. We'll take some audience questions, and we'll record it all as a live episode of the podcast. It's going to be great. Syzygy is produced by me, Chris Stewart, here in Emily's office at the University of York, and we're very thankful to the University of York for giving us the opportunity to do this. And we will be back again in about a week's time for another edition of Syzygy. Not sure what we'll be talking about yet. I think we'll take a bit of a break from black holes and go to something else in the universe. But whatever it is, it's going to be fun. We'll see you in a week's time.
See you later.
Bye.